So there will be times on an AP test when you're asked to find a Taylor polynomial for a function f. However, there are going to be other times when they give you a Taylor polynomial and they ask you to interpret what is going on. So notice in this case, the question is saying, let p of x be the third degree Taylor polynomial for a function f of x. And we are first asked, where is the function centered? So we need to be able to look at this formula and look at the polynomial and know what all of its pieces represent. In other words, notice we need to know the formula and where it came from. So notice each of these terms has an x minus 3. We should be thinking that's shifted to the right 3, so this polynomial is centered at 3. The second part asks us to evaluate f of 3 and f prime of 3. Since we do not have f, we have the third degree Taylor polynomial for f, but we should recall that since this is centered at 3, the formula for a Taylor polynomial would be f of 3 plus f prime of 3 times x minus 3 to the first power. So when I look at this, I know my first term should be f of 3 plus f prime minus x minus 3 plus my second, f prime of 3 plus my second derivative at 3 divided by 2 factorial times x minus 3 squared, and so on. So when I go to evaluate f of 3, it's right here in my Taylor polynomial. F of 3 equals 4. And when I go to find f prime of 3, I need to recognize that that is my 2. Notice in part C that we are asked to use the first 3 terms of p to approximate f of 3.1. So it doesn't say to use the third degree of the polynomial, but the first 3 terms. So we have to be really careful here. Sometimes we're told which degree to use. Sometimes we're told how many terms. So the first 3 terms of this polynomial are going to be the constant, the linear term, and the quadratic term. So we won't use that 4th cubic term. So I know that my polynomial is an approximation for f of 3.1. So I'm going to replace x with 3.1, and I'll get 4 plus 2 times the quantity 3.1, minus 3 to the first power, and then minus 4 times the quantity 3.1 minus 3 squared. All right, so to evaluate that, I have 3.1 to the first power, 3.1 minus 3 to the first power, so that's just 1/10. So I have 2 times 1/10, or 2/10. And then I have minus 4 times 0.1 squared, so that's 4/100. All right, so we could get a GCF here of, I could actually reduce this first. I could think of this as 4 plus 1/5 minus 1/25, and I could get a GCF here of 50. Actually, I could just get a GCF of 25. So 4 times 25 is 100. 5 times 5, so 1 times 5, I'm going to get a 5 there. All right, so we end up getting 104/25. So that is our approximation of f of 3.1. All right, so finally, we are asked to evaluate the third derivative at 3, f triple prime of 3. And we want to be careful here because remember, when I get to my third term, that 1/3 isn't f triple prime of 3, but that 1/3 is f triple prime of 3 divided by 3 factorial. So really, I could multiply 1/3 by 3 factorial. And that would just give me 2. So the other thing that AP will sometimes do with Taylor polynomials is they might just give us a table and ask some questions. So notice this table is a little bit different. So notice it's telling us that when n is 1, that means that this is the first derivative at 0. So this n is telling us what derivative we're taking. Also, as I go back and kind of read this question, f is a function with derivatives of all orders at x equals 0, such that f of 0 is 2. So I could think of this as being centered at 0. So this is telling me my first derivative of 0 is 0. This 2 is telling me my second derivative of 0 is 4. My third derivative of f of 0, or at 0, is 3. And my fourth derivative of f at 0 is 8. So we just have to be really careful here when we're reading this table that we realize n is not our input. It's not our x value that's changing. It's the order of our derivative that is changing. All right, so if I want to find the 4th degree Taylor polynomial, it's going to, again, be centered at x equals 0. So I know I'm going to start with f of 0 that they're giving us. And then I'm going to add to that f prime of 0 times x minus 0. Well, that's just x to the first power, plus my second derivative at 0 divided by 2 factorial times x minus 0 squared, so times x squared. Then I will get my 3rd degree derivative at 0 over 3 factorial times x cubed. Then my 4th derivative at 0 divided by 4 factorial times x to the 4th power. All right, so when I go ahead and write that out, that is 2. Remember they told us up here f of 0 is 2, plus, well, f prime of 0 is 1. Or sorry, f prime of 0 is 0. I read my table wrong. So I get a 0 times x there. My second derivative, we said, is 4, but I'm dividing that by 2 factorial and then multiplying that with x squared. My third derivative is 3, but I'm dividing that by 3 factorial, multiplying that with x cubed, and then my fourth derivative is 8. Oops. But I am dividing that by 4 factorial and multiplying that by x to the 4th power. All right, so if I write that out more neatly, we get 2. We had 0x, so when I get to my quadratic term, 4 divided by 2 factorial is just 2, so I get a 2x squared, plus 3 divided by 3 factorial is 3 over 6, so that is 1/2 x cubed. 8 divided by 4 factorial, sometimes I have to do these out to the side. Remember, 4 factorial is 4 times 3 times 2 times 1, so 8 divided by 4 would leave me with the 2, but then I could factor out the 2, and I get 1/3. In part B, We are given g of x equals f of x squared, and we're asked to write the 6th degree Taylor polynomial for g at x equals 0. And there is a hard way to do this, and there's an easier way to do this one. So there's two ways to do this one. So let's look at what we could do. And spoiler, this is not the easier way. So if I wanted to find the 6th degree Taylor polynomial for g, I would need to start with like g, so g of x, g is equal to f of x squared, and remember we're plugging in a 0 for that. So like g of 0 would be f of 0, for example, which we know is just 2. But then I would also need my first derivative. Well, I'm going to need a lot of derivatives. Well, I would need my first derivative, g prime, and I would have to remember to use the chain rule here. So when I take the derivative of f of x squared, I would get 2x f prime of x squared. So then when I get to my second derivative, now I'm going to have to use the product rule. So like my second derivative of g gets pretty gnarly, and I get 2f prime of x squared plus 2x times 2f double prime of x squared. Oh man, I'm forgetting the chain rule here. Sorry, 2 times f prime of x squared plus 2x times another 2x times my second derivative x squared. That second 2x is from the chain rule. So this starts to get pretty gnarly pretty quickly. We could do this and we could get our Taylor polynomial this way. But we could also just use this relationship between f and g. So if g is equal to f of x squared, and up here, this polynomial that we got, our Taylor polynomial, this is an expression for that, this is a polynomial that approximates f of x. So f of x squared is just whatever we get when we plug in x squared into f instead of x. So we could replace the x with an x squared from our polynomial here. So we would still have our 2. Actually, I should circle this one that we wrote in simplified form. All right, so we would still have our 2, but when I get to 2x squared, I'm replacing my x with an x squared. So I have x squared squared. My next term is 1/2 x cubed, but now I'm plugging in an x squared, so 1/2 x squared cubed. And what I might notice is that x squared cubed is x to the 6th power. So this is the 6th degree Taylor polynomial. I don't need to use that next term. So when I go to write my approximation for like g of x, I get 2 plus 2x squared squared is 2x to the 4th power. And then this last term, 1/2 x squared cubed, is 1/2 x to the 6th power. So again, it's easier to use the polynomial that we already found and just replace x with x squared. In part C, we're asked to find the 5th degree Taylor polynomial for g prime of x about x equals 0. Well, again, notice that in part B, we wrote a 6th degree Taylor polynomial for g. So when we're going to find g prime, we could again just use what we wrote in part B. So g prime of x is going to be, well, the derivative of 2, my constant is 0, but my next term, 2x to the 4th, I would get 8x cubed, plus my last term, 1/2 x to the 6th becomes 3x to the 5th power. So that is a 5th degree Taylor polynomial for g prime of x about x equals 0. Finally, when we get to part D, this is something they throw out there every once in a while. We are asked if the graph of f has a relative maximum, minimum, or neither at x equals 0. So I can't, I don't actually have a function for f. The polynomial approximates f, but I don't have a function for f. So I can't find critical values, and I can't use the first derivative test to determine if there's a maximum, minimum, or neither. So what I need to do is use the second derivative test. So I would first need to know that f prime of 0 is 0. And we are given that, again, in our table up above. So I know that f prime of 0 is 0. Then I would also need to know the value of my second derivative. So my second derivative at 0 is 4. And 4 is a positive number. So that tells me that whatever f looks like at x equals 0, f is concave up, so at x equals 0, and the value of its derivative, its first derivative, is 0. So I know that I would have a horizontal tangent line there, but since my second derivative is positive and my graph is concave up, that means that I must have a relative minimum there. So again, to justify this, I would say f has a relative minimum at x equals 0 because f prime of 0 equals 0 and the second derivative of the second derivative of f at 0 is positive. So in general, when we're asked about relative maxes and mins and we're working with Taylor polynomials, we are most likely going to need to use that second derivative test.